Welcome everyone to the afternoon session. We have Federico Rodriguez-Hertz from Penn State talking about rigidity for Anosov higher rank lattice actions.
Okay, thank you very much, and thank you, the organizer, for inviting me and giving me the opportunity to speak in this beautiful conference. So let me start with the topic of the course. So let me first start with the smooth dynamical part of this talk. Okay, so this is about Anosov actions. So let me say what is an Anosov system. So we have a diffeomorphism. And we say F is Anosov if the tangent bundle splits as the direct sum of two invariant bundles and the dynamics of F contracts the stable guy and the inverse contracts the unstable guy. Okay, so this is very standard situation, and main examples of such guys are any matrix in this GL DZ induce an automorphism of the torus, which if whenever A has no eigenvalue of modulus 1, you get this Anosov system. And this can be accordingly generalized to nil manifolds which is same thing, so you quotient your simply connected nilpotently group by a lattice, and then take a linear guy. Yeah, I will not call it A because it will be the same as lambda. So we can automorphism preserving the lattice, and then it will induce an automorphism of on the quotient space. And again, if you don't have eigenvalues of modulus 1 for the ad of L, then you will get, for the derivative of L, at the identity, you will have that this is, again, an Anosov diffeomorphism. And the same thing can be done if you take some finite quotient of these nil manifolds. These are called infranil manifolds. Where F then will need to be a subgroup of affine maps of N, which make everything commute so that you can induce some dynamics there. And so far, these are all known examples of Anosov diffeomorphisms, and it is conjectured by smele that this is all. So is every Anosov diffeo is topologically conjugate to an infranil manifold automorphism, which has to be Anosov by general nonsense. So this conjecture is widely open still. So, and the main problem is to show that the manifold M is actually an infranil manifold. So the best result, essentially the best definite result toward this direction, there are other partial results which are very important in this theory, but the best result is by Franks, Sean Franks, and Anthony Manning. Well, each one contributed to one part of the theorem, and there should be an S here, I guess, which says that if M is an infranil manifold, and F is Anosov, then the conjecture is true, meaning that it is really conjugated to an automorphism. So really the problem here is whether the manifold is an infranil manifold. So there is the equivalent notion of expanding map, where then it's just a covering map. There is only expanding bundle. And you have the same examples essentially. And then the conjecture is not a conjecture, it's a theorem where Shoup proved this statement essentially. It was his thesis. And then the result of Gromov on groups of polynomial growths implies that the manifold is essentially a nil manifold, and then you are done. So that's what is known about one system. And there is the same conjecture or similar conjecture in more general situation of larger group actions. So, and that's what I will discuss now. So later I will comment when the group is just an abelian group with rank larger than 2, because this is larger or equal to 2, which is an important ingredient of what I'm going to discuss. But so far, let me put the setting which I will be working. So gamma is a lattice, and G is a semi-simple Lie group with all factors, almost simple factors, yeah, simple factors of rank different, of real rank different from 1. So you can, compact factors are not bad here, but rank 1 factors are really bad. And since all simple factors are of rank different from 1, really is not needed to assume gamma is irreducible. So since it will project into nice guys if it is reducible. So then, in definition, we have gamma acting on a manifold M by an action alpha by diffeomorphisms. So we say, well, of course, the definition can be done without the assumptions here, but anyway, we say alpha is Anosov if there exists gamma naught in gamma such that alpha of gamma naught is an Anosov diffeom. Okay, if there is one element which has the Anosov property, the hyperbolic property, then you call the action Anosov. So yeah, maybe just for the non-fully homogeneous people, so you can assume without loss of generality that gamma is SL3Z and that G is SL3R. Already there, the results are new and as well shows all the problematic that could appear in the general situation already appears in this SL3Z situation. So the non-co-compactness and whatever thing, even I would say that philosophically, this is a little bit harder than the other cases because it's too small a group, so in principle. But still. Okay, so then the corresponding conjecture, which I haven't read really the attribution, but I think it's reasonable to attribute it to Zimmer. Who else, after all? So, which is the same conjecture as for smele, but in this context. So, if gamma is Anosov, then alpha is, let me just put that this way, essentially algebraic. Depends on what you want to understand. You can just call it algebraic, depending on how you want to think it. So, which means there exists such a quotient, well, H from M to F mod N mod lambda, smooth diffio, and rho naught. Let me put some embedding of gamma into affine guys on this quotient space, which is guys that live to the nilpotently group out as affine maps, such that H compose alpha gamma compose is the same as rho gamma compose H for every gamma in gamma, which is the natural notion of isomorphism in dynamical systems. So, capital F is some finite symmetry group on the nil manifold by affine system. So it already is the infra-nil manifolds. So examples of this is like the Klein bottle, where you have the torus and then you just have some finite automorphism and you go to the Klein bottle. Essentially means that there exists the H, which is a diffeomorphism. So it's smoothly conjugate to algebraic. Okay, you can call it algebraic if you wish. So there are some, I don't know, I'm not an expert on this part of the world. There are some delicatessen, I guess, about whether if you have a smooth diffeomorphism really has to be realized by an automorphism or by an affine map or something like that, which then I guess it's fair to call it algebraic, but I'm not going really into this part. Okay, so that's the conjecture. So let me then state the theorem, and then I can move on and describe the the problems and what needs to be done in this setting. The theorem is joined with Aaron Brown and L.wang. It says that, there is, maybe I should comment here in Frank's Manning theorem and as well as smele. So in smele conjecture, so it's considered is topologically conjugate to an infra-nil manifold automorphism, and the same expanding map theorem, it says that it's topologically conjugate to an expanding map, an expanding automorphism. So there are examples by Farrell and Jones, and then later by Farrell, Jones, and Gogolev, that show that M may not be diffeomorphic to an infra-nil manifold, maybe just be homeomorphic to an infra-nil manifold with a different smooth structure, and still supporting an Anosov diffeomorphism. Okay, so here, when I say M is an infra-nil manifold, you only need to assume it's topologically equivalent, so it's homeomorphic to an infra-nil manifold. You don't need really to assume. So same assumption we do. Assume M is homeomorphic to an infra-nil manifold. And assume gamma acts on M is Anosov. so gamma is this lattice I was mentioning. Then alpha is algebraic, or essentially algebraic. Just do the short. Okay, I said essentially, so let's keep on saying essentially. Algebraic. Okay, so it's the similar result here, but you have not just a topological conjugacy, it's a smooth conjugacy, which in particular said that the infranil manifold is actually a smooth infranil manifold, not just a topological guy like this type of examples. So other way of interpreting this result is, and I think that's what's really in Zimmer type of program, is that there are no non-algebraic actions when it comes to larger groups. So it's only the algebraic. So in a sense, for homogeneous dynamics should be good because it means that no one should go outside of homogeneous dynamics if studying this action. Okay, so let me tell you a little bit of the history. There are two histories to tell about this theorem. One is what are the previous results, of course, and the other is how we end up in this theorem. Okay, so let me just try to briefly summarize the previous results. It will not be a complete list. I just want to highlight 3 works which are relevant. And there are also several very important work when one does not assume that the manifold is an infranil manifold, and then you put a lot of hypotheses on the action and still get the same result. But I will not discuss them because this will take me completely out of what I want to discuss. So, so the first results on these directions are, and the most important one in this direction was by Katok, Lewis, and Zimmer, where they did the case that gamma is indeed SL and Z, and it acts on the torus Tn with an Anosov element. And they assume there is an invariant measure. They fully supported indeed. Invariant measure. And the reason for that is clearly there is the name Zimmer there. So the first thing you do when you have such thing is to try to apply in one way or another Zimmer cocycle super rigidity. And for this, you want the invariant measure. Okay? So I want to emphasize that we are not assuming any invariant measures in our result. Not fully supported, not nothing. But still, so when we approach it, we wanted this invariant measure very badly, and we really worked a lot of our time to find this invariant measure. And this, even though was useless for this problem, it was very useful for other problems that we also were studying. So the next results are by Margulis and Kian. Where they did more general lattices acting on still the torus Tn, even though one can fairly generalize what they did. They also did nil manifold indeed, yeah. They also did this. And there were, of course, I'm not discussing the local theory when you are just a perturbation of the algebraic action, where then there is Fisher and Margulis, which fully finish the local rigidity problem in full generality. So this is like a semi-local type of situation. So they put some strong conditions on the action, which are transversal to the Anosov condition. So you ask to have a lot of bundles with hyperbolic properties, And they still assume assuming the fully supported invariant measure. So they still make it, and with assumption on the nonlinear action. Yes, then Fisher and collaborators also generalized a little bit this result to not on this conjugancy problem, but on some cocycle part of the problem, but still always assuming this fully supported invariant measure. And here there is an extra hypothesis which was very annoying to everyone, even also to us. When we published the paper, we still had this hypothesis that I'm going to list there, which is a completely annoying hypothesis that finally we removed. So, which is that the action lifts to an action on the universal covering. So it's on one hand, it's not such a bad assumption, since if you have a fixed point for the action, then you are fine, because you can lift every element to the guy that fixed this point, and then this will be still an action of the universal covering. But if you don't want to assume the existence of a fixed point, because a fixed point problem for actions is very hard, so then still you can translate the problem into a problem of vanishing of second cohomology, and then there is a lot of results on vanishing of second cohomology, which will make that every co-compact lattice is okay, and then you have to go each lattice for each lattice and see whether you are in the list of vanishing or not in the list of vanishing, and well, there are a lot of lattices that don't enter in that list, and then who knows. So then it's better really a slightly different solution where you just, so I will try to explain it a little bit better, but so one part of the proof of the theorem goes into some vanishing of first cohomology, and vanishing of first cohomology is a little bit simpler than vanishing of second cohomology, and so that's good enough for the lifting problem. And as well, this bypasses the use of the invariant measure as well, so okay, so so then let me just tell you how we started thinking on this problem. So we prove with L.wang that if you have a ck action, c square is good enough, k larger than or equal to 2, on, again, an infinite manifold which has an Anosov element, plus another hypothesis that I will not explain exactly what it is, at least not yet, which is no rank 1 factors. But it's a very natural hypothesis, which certainly appears in all measure rigidity type of statements, and certainly as well in smooth rigidity. Then we show the same statement, so we call it alpha, maybe alpha, yeah, let's still call it alpha. Then alpha is essentially algebraic. Okay, and again, it's only needed that the manifold be homeomorphic to an infinite manifold. There is no need to blah, blah, blah. Okay, so once we have this result, David Fisher and Ralph Patzier asked us why you don't just go and prove this, so you already get the smooth conjugacy. So you put it as a corollary down there. But the first problem show up, that is, you don't know where your Anosov element lives. So you have your gamma naught, where alpha of gamma naught is Anosov, but the gamma naught, the centralizer of gamma naught may be rank 1, maybe just one line. So as trivial as that, and that's exactly what happened in SL3Z, when you have a matrix which has one pair of complex eigenvalue and the other eigenvalue has to be real, then the centralizer is just powers of this matrix, essentially. So it's Z, maybe plus minus identity. No, it's 3 dimensions, so minus identity is not there. But anyway, so it's just a line, so you don't have your CK action there. And then even more in general, so even if you have your CK action, so if you really manage to have the K larger than or equal to 2, there is this no rank 1 factor assumption, which is as well not trivial to get, so just from nowhere. So you have one Anosov element and you have to produce another Anosov element from somewhere that will satisfy this hypothesis. And you have more than one Anosov element because you can iterate your Anosov element, you can conjugate this Anosov element by elements in the group, so that's fine. But this will not produce any better algebraic properties of your gamma naught. If you conjugate, you still have a small centralizer and still you have rank 1 factors. So you really need to produce a seriously different Anosov element. So that was one of the big problems, but then the second problem as well arises, and this is why it's so important here, the invariant measure, which is you use this Franks-Manning conjugacy, and you know that this guy is conjugate to some linear guy, but by a homeomorphism. So you can linearize by a homeomorphism. But then this H gamma naught will depend on gamma naught. So if you take a power of gamma naught, it's okay. But already if you take a conjugate of gamma naught, then the H will be modified. So there is no reason why the guy that works for this gamma naught will work for any other element of the group which is not commuting with gamma naught. So this is the second problem, and when you see it a little bit, you can recognize that eventually this is just a cocycle problem. So you really need to kill a cocycle. So, so let me then state these two main ingredients. Essentially, it means, let's just, because the rank 1 factor is about the linear, so I should speak what is the linear action first, but imagine you have a linear action, and I will describe what is the rank 1 factor for a linear action. So essentially, it means that you have, I already used L, so let's call it L, from ZK, a homomorphism into this rank 1 group, and your rho of n will be of the form 1 matrix to the power L of n in the first coordinate, and in the second coordinate you will have some linear, the rest of the guy, so some beta of n. Okay, so you have this A is 1 matrix in SL D1Z, say, and you are in torus TD1 times torus TD2, so you have that I'm just doing the torus, the nil manifold, infinite manifold is the same type of structure. So your torus split as a product, and you have this factor onto the first coordinate, which is just iteration of 1 matrix. Okay? So you don't have other guy. So this is a rank 1 dynamics, so this is the rank 1 factor. But the hypothesis indeed is the linear is for the linear part. So let me define what is the linear part. So let me, from now on, just to make my life simpler, assume that all the time the Lie manifold is t to the power d. So let's just do the abelian case. The other case you do as always, take some covering to get rid of the finite part, then go through the tower and do the job. So, so then you have t to the d. So then you have alpha is your action from gamma into this t to the d, which even if it is topologically t to the d, what I'm going to do now, it makes sense. You have rho, which is the same as alpha star, or even in this case I could put alpha star, but anyway, which is the action of gamma, the induced action of gamma on the automorphisms of the H1 of TD, which is nothing but GL DC. Okay, so this is a corresponding linear action, which is the action of the guy in the first cohomology group of the torus TD. And what's important of this is that for every gamma in gamma, you have that alpha of gamma can be written as rho of gamma times identity plus some phi gamma, where phi sub gamma goes from TD to TD, is homotopically trivial. Okay, so every map on the torus can be written as linear plus the periodic term, and then that's rho is this alpha star, which is this rho gamma. I think I'm doing things correct. I prefer to do the action on the first homotopy, but then you don't have the fixed point, so you have to explain that the first homotopy is abelian, and then eventually you end up there. So it's more or less the same. Okay, so this is this phi gamma. And of I wanted then to describe these two steps. So step one, which is exactly related with this phi gamma here, is vanishing of Wanko cycles. Of course, I should explain exactly what type of Wanko cycles I will care here. So we have twisted coefficients. I will describe later what are these twisted coefficients. And the step two is producing a Zariski dense semigroup of Anosov elements. These are essentially the two steps which will address our discussion. So let me explain briefly, and then I go through the details, how these are supposed to address. So if I delete the gamma naught and take out the zeros here, so I will show in a second, hopefully, how this equation becomes a cocycle equation, and the vanishing of cocycle will solve this equation as a continuous map, homotopic to the identity. So H will be just continuous and homotopic to the identity solving this equation. And then there's some uniqueness for the gamma naught, and for the gamma naught is a topological conjugacy, so this H will become a homeomorphism for free by Franks and Manning. So this is the step one, which is you get a homeomorphism that trivializes your guys. Now, the second step, as I said, is the gamma naught is Anosov, but it's not good enough for this property k larger than 2 and no rank 1 factor. So you would need to produce another Anosov elements, and Anosov element with some property. The properties are these that are listed here. So then you go to the literature, and you first learn even the basic, which is Raghunathan-Prasad, which tells you exactly when a lattice hits the Cartan subgroup. And that's exactly what they do. And then you have more detailed versions of this, which is Prasad-Rapinchuk, which holds for Zariski-dense semigroups, and tells you exactly that these Zariski-dense semigroups will hit the Cartan subgroup. So this is not anymore a problem if one produces this. But then you have to go to the rank-1 factors. So one has to twist a little bit and work a little bit further on what Prasad-Rapinchuk do. But it's just following what they did, and just you push a little bit further their proof, and you show that essentially the elements they are finding not only hit the Cartan, but also hit the Cartan with this property as well. Okay, so maybe with an extra Zariski openness, but that's okay. And so then you produce your gamma 1, which is Anosov, and the linear pair has no rank 1 factors, and once you achieve that, the H becomes smooth by our theorem, and then you are done. Of course, there is a lot of subtleties here, which I'm a little bit hiding. You go only finitely many times, but it looks like if it were infinitely many often, but it's only finitely many times through finite index subgroups. So you still have your guy doing this construction. And then you eventually get an action by automorphism, not by affine maps. But whenever you conjugate to automorphism on a finite index subgroup, then you are conjugate the total action to affine action. So that's a very simple finiteness type of business. It's more than regular. You have to be regular also with respect to Galois conjugation on your guys, on your elements. Okay, so essentially you want that the Galois group contains the veil group, and once you get this, you essentially are fine. So it's still it's a notion of regularity. So it's not the definition of regular in Raghunathan-Prasad, but it's a notion very similar to this regularity. So yeah, you will assume they are regular, that they are hyperregular, that they are irregular, and then this extra assumption, and you get this no-rank factor. Okay, so let's go to vanishing of cocycle. So how this equation goes. Let's keep the results. Okay, so the first observation is that this phi gamma 1, gamma 2, so it has this cocycle property, which I will just denote in this way. Wait a sec. This is phi gamma, no, I think I'm doing it right. Where what is beta gamma? Beta gamma of phi is rho gamma inverse times phi compose alpha gamma. This action, and this beta gamma, which is not exactly the beta gamma I really want, but it's roughly speaking the same. So this beta is a representation of gamma into linear guys, so to speak, of Z0 TD. Okay, so yeah, this is not a Banach space because it has values in TD, and I really want a Banach space. So the beta I really care will be a little modification of this beta here. But this, you just look at the group action condition and the definition of phi gamma, and you see that they satisfy exactly this equation. So, so what does it mean that this phi gamma, so this phi is a function from gamma into this Z0 TD and TD, and phi is homologous to 0 if there exists a function B in Z0 TD such that phi of gamma, or phi gamma, is the same as B minus beta gamma of B. Okay, so that's the natural definition of being homologous to 0 for a cocycle like that. So the D operator for this is just take minus here. This is the D operator of this, and the D operator of a B is just this. And if I did my computations correctly, I should have that if you take such a V, you define H as identity plus V, and you will have that H composed alpha gamma is rho gamma composed to H, and this formula is exactly the same as this formula. I leave it to you as an exercise, but it should be the most straightforward property ever. Now, the problem with this is that typically you want to have cocycles which are valued not in these TD guys. You want to have some modular, better if you have some vector space. So then I want to modify everything and be able to put an RD here, an RD here, and an RD here, and still claim that it's the same. And certainly if I can do it, then I also solve it. Now, what's the problem with this is the lifting property. So I don't know the action lifts, which means that when I do this equality here, I don't really have full equality. I get plus some n of gamma 1, gamma 2. So I can still lift the individual elements the way I want, just lift them individually. And then you look at the fact that you come from an action on the torus, and you see that, well, you are essentially a cocycle, but you have this mistake there, which is a 2 cocycle, ZD value 2 cocycle, and then that's why you enter into this n being H2 with of gamma in this Z, D twisted by the rho, and it's a question about vanishing of this guy. Then you put all your machinery and kill this guy. That's one thing to do, and we were very heavily trying to compute this homology using null reference, and I have to confess that it took to me 2 years to just realize this stupidity, which is that this guy is essentially the same as this guy. Okay? Which the problem of this quotient is that this is not giving you a Banach space, because it is not a vector space. So 2 years to change ZD to RD, and now it's a Banach space. And then you're happy. Then you quotient by RD, you gain a cocycle again. Then, of course, the last step needs to epsilon work that I can describe you in a second. But this is really very trivial. And you are done modulo proving the vanishing of cocycle theorem. So you have the vector space. So the theorem then, this is very axiomatic approach, so you don't really need the I just quotient this by RD. Yes. No, it's to TD, to RD. So it's function from the torus to RD, and then you quotient. So these are not anymore functions. So it's functions up to a number, but it's still a nice Banach space. Yeah, no, it's not. It's different. So yeah, okay, yeah, no. Here is now it's not anymore the same. Yes, it's not anymore the same. I completely agree. So it was the same before, but now it's not anymore the same. So you had to just forget about this guy, forget about your functions, just go to this Banach space, solve whatever you have to solve in this Banach space, and indeed, yeah, let me just show you, because it's very brief, what is left. So, and then I state the main theorem of the step one. So what you do, you get your V, and V now is an element of Z0, TD, RD, mod RD. Okay, so that's the solution you got is a vector there. Now if it is a vector there, it's as well a vector here. Okay, you just pick a representative and that's it. The important is that this equality is in the quotient. Okay, which means that phi gamma is equal to B. Now phi gamma, I'm not taking the quotient, is V minus beta gamma V plus some C of gamma, where C goes from gamma into RD, is a one cocycle. And it's a one cocycle because it's the sum of two one cocycles. Phi gamma is a one cocycle, this is another one cocycle, so it's a one cocycle, maybe take a value into function spaces, but it's a constant function, so it's just really this, which means that this C is an element of H1 gamma RD still rho, but this is 0. And you can use general theory, or you can go back again to the first theorem, and in particular, you can apply for this Banach space, which is RD, with the coefficients twisted. And, then this is 0, which means that, well, you need to take a finite index subgroup then. So this implies that some non-trivial, some trivial shock indeed. There is some gamma naught, and it vanishes there. So C is 0 when you, well, you have to work a little bit here, but essentially you show that it's really, you can make it take values here in the integers, and by taking a finite index subgroup, it will be really 0 there. And once it is 0 there, you just make your adjustment here, and you are done. So, okay, so what's the theorem? So you have gamma, which could be that gamma we were playing there, or satisfy 4 conditions, which are very basic, indeed not just on gamma, but as well, and that's very important, that is on this beta. Now B is a Banach space, you have linear on Banach spaces, and you have this rho as well, which is a finite dimensional which is not important in the statement, but is important in the proof. So satisfying these 4 conditions that I hopefully will describe in a second. The 4 conditions are fully satisfied as soon as gamma is a higher rank lattice and rho is a representation with an Anosov element. Then this is automatic. These 4 conditions I will describe, but maybe gamma is not a higher rank lattice and still you can. So it may be SL2 cross SL2, but the representation is nice. So you may still have these 4 conditions. So then H1 gamma the rho is 0. So that's the statement. Of course, if I not tell you what are these 4 conditions, this is almost a vacuum statement. So what I want to emphasize is that, so this is a Banach space, and the Banach space we are caring here is Z0, so it's certainly not a nice Banach space to do cohomology of higher rank lattices. So the spectral gap, if you wish, comes from rho. That rho is hyperbolic. Okay, so there is where really comes the strong property. We are working with Sheeran and a student of Sheeran as well, so we can relax pretty much the hypothesis here, which is in this situation we are discussing there, is the hyperbolicity of the element, so that there is an element which is fully hyperbolic. We essentially think that we should be able to relax it to just assuming there are no invariant vectors. And then, of course, you can always split your representation, your final representation, as the invariant vectors and the non-invariant vectors part. So the non-invariant vectors part, you can have full vanishing for whatever Banach space you want, essentially. And then, of course, the finite vector, we need a Hilbert space. So then you can always solve it, but only at the measurable level. And the point of this vanishing is what allows you not to play with invariant measures. So you really are only using the C0 structure, so you don't care about invariant measures. You don't need the L2. So what are these four conditions? Only one is really the most important of all. I hope I remember all of them. Okay, I think 1 and 2, I can resume them in essentially saying that beta is rho tensor pi, where pi is isometric. And rho is finite. So rho is induced from a representation from G is a finite representation. So that's so there is a more axiomatic, but I think that's good enough, which is exactly what is happening here. Is the rho tensor decomposition by alpha, which is isometric. So then the third is very important, but again, it holds in all the type of examples, which is gamma. The embedding of gamma in G is quasi-isometric. Which is nothing if you are assuming that gamma is co-compact, or in this higher rank situation, again, it's nothing, but by Lvovsky, Moses, and who is the third one? Raghunathan, thanks. Yeah, I'm saying nothing because the theorem is already there. So it's a very hard theorem, but okay, we have it already. So in this situation, this is done. Indeed, it's lack of knowledge, but luckily we learn. So we would stack a lot of time because thinking of SL to Z in SL to R, which is not quasi-isometric, and nothing worked until we realized that life is nicer than SL2. And the fourth condition is the non-resonant condition. So what is this non-resonant condition? Which one should relax it if one wants to go further than the type of actions I'm analyzing here, but I don't want to do that. So, okay, so you have the set of roots and weights, so let rho from G into GLDR be a representation. And let chi be the set of weights, restricted weights of the representation, which are essentially the Lyapunov exponents for the people doing smooth dynamics. So these are just the Lyapunov exponents of the diagonal, whatever diagonal group is in here. So you diagonalize and are just the logarithm of the eigenvalues of the guy. So you have then the roots, the set of roots of G. And given any root, you have the root space, which I should call it in some way. And I think ER is a good name for it. ER is root space, which is the subspace of the Lie algebra of G, where the root is happening. And so, okay, that's our just notation. Then we say R is resonant with rho if there exists chi a weight and a constant z positive such that chi equals to z times r. Okay, so if you are a multiple, a positive multiple if a weight is a positive multiple of a root, then this root is resonant. It's resonant with the weights. Okay, and the typical example of a resonant weight is when you have that joint representation, then indeed all weights and all roots are resonant. So each root has a weight because the roots are the weights of the adjoint representation after all. Okay, so resonant roots are not good for this business. And indeed, this was the key step. So once we understood that this was the crucial notion, so all this theorem just went at once and all the finding measures went on at one. And it really came from a very strong discussion of what is the difference between the standard SL and Z action on the torus Tn and the projective action of SL and Z on the sphere Sn minus 1. So why one has an invariant measure and the other doesn't have an invariant measure? Why one is Anosov and the other is just everything is contracted to a point? So what was really the main difference, and we were really struggling very badly to, so what will distinguish between them? So it's who distinguishes them? And yeah, then we went to sleep, and the following morning, Sheeran came and said, okay, the projective action, all the roots are resonance. For the total action, all roots are non-resonant. That's it. So that's opened the door, and all the rest went through. So, so what's the non-resonant condition? So we say rho is non-resonant if the Lie algebra of G is generated by the non-resonant root spaces. Okay, so non-resonant root spaces are here is the definition of resonant roots. So you take the non-resonant roots, which are the ones not having any weight being proportional, and you look at all these spaces, and you want this to generate, and the reason for that is you can prove something happening along these root spaces, and you want this to give the whole Lie group. And that's exactly the condition you put. And the magic is, and this is just coming from the theory of highest weight, is that if you have this Anosov property, you have an hyperbolic element in your representation, then there may be some resonant root because life is not as nice in the world, but essentially most roots are non-resonant, and that's because you go from the high weights and you start removing roots. That's how you get. So if you reach a resonant root, then you will reach zero, because you continue deleting this root. Then you have half roots, and then this is a pain. But still, you go through all the descriptions, and you still can check that in this non-zero weight condition, you still generate. And then you are happy. So the fourth condition is as well good. And then you have your theorem, which is just vanishing of the cocycle. So how you prove this theorem? So this means I have 5 minutes.
More than 5 minutes.
Okay, so it's rather than that. Okay, not that bad then. Okay, maybe let me. Let's not waste time. Let's start erasing. So, so then the way you solve this equation is by very standard type of construction. So you take G mod times B mod gamma, take this bundle where you identified GB with G gamma, and then here you would beta gamma B plus phi gamma, So that's the standard, and this bundle is a bundle over G mod gamma with fiber B. And then you are looking for a section for this guy, but not any section, a G invariant section. So you are looking for essentially G, where H sub G belongs to B for every G. We satisfy the whatever identification here, which should be H sub G gamma is, I guess, beta gamma HG plus phi gamma. I guess that's what comes from there. That means that this is a section, but you want it to be as well G invariant. So G invariant, which means HAG equals to HG for every A. In G, and of course, saying this is like a stupidity, so this implies constant automatically, because this means that everyone is like H on the identity. So this would imply that HG is H identity for every G. So, but still I prefer to formulate it in these two steps. Now, solving this first is almost impossible. So this implies studying some, again, vanishing of some higher cohomology, and blah, 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 which is really, it makes it almost impossible from general topological nonsense. So it means that really this is a trivial bundle, which, yeah, really there is no reason why it is, but what you do is just remove it for every, and you put just for every, almost every G with respect to our measure. Okay, and then you want everything to happen G almost everywhere. Okay, and then still eventually ergodicity will tell you that this is just one map. So, but let me emphasize that here the only variable is G, so it's almost everywhere with respect to G. Okay, then producing this guy is quite easy. So you just take your fundamental domain for the G mod gamma, and you define H bar as being 0 on sigma and extend to G in the obvious, so that this is true. So this gives you a piecewise nice guy, so not continuous, but is well defined almost everywhere, satisfying 1. And then you take A, your Cartan subgroup, you pick A naught in G generic, if you have seen the proof of Hartmann-Grobman, that's exactly what they do. Well, indeed, I have to do epsilon more to do exactly what they do, but that's essentially what you do. You take the iterates of these guys, and you show that this is a Cauchy sequence. Okay, now there is some problem to do that. So for almost every G. So there are some problems to do that, and the reason for that is that you have your A naught, you have your rho A naught. This is a map from RD to RD, a linear map, so it has a splitting, and that's the genericity assumption as ES plus EU. So this will be a Cauchy sequence if you take the S part of this guy and take it N positive. And it's indeed better than Cauchy, so you have a very precise description what these are, these iterates. These are essentially rho A naught to the N of H bar S G. Maybe there is some trash here that I'm not wanting to discuss, but that's essentially what it is, roughly speaking. And then you know this is a contraction. I didn't put exactly the cocycle, but that's more or less what happens. So when you try to show is a Cauchy sequence. And the problem is that there is the G there, so there is some problem in a sense when you go to the cusp, which here the cusp has to do with the irregularity of this HG, But, well, some integrability condition coming from this quasi-isometric property will give you that you return to bounded regions often enough so that you really get for almost every guy a Cauchy sequence. So it's a very, very basic result and very basic computation. So you do this for n positive in the S part, you solve it for n negative for the U part, and then you have a solution for the A naught. Now, indeed, the construction is a fixed point property, so the solution is essentially unique. Of course, unique in the setting you are working on it. And so once you have this sort of uniqueness, you work epsilon more and you show that the same guy is invariant by the Cartan subgroup. So the invariance, in principle, was just invariant by A naught, but then you can upgrade it to every guy in the Cartan subgroup, and indeed it's even better than the Cartan subgroup, it's by the centralizer of A naught. But since I took a generic element, so the centralizer will just the Cartan. Then you go to a root space, and you take an element in a root group, and you want invariance by this root group. And there is where the non-resonance appear. So you essentially get that this guy will commute with some guy in the Cartan by the non-resonant, and in the fiber they will do the opposite that you are doing in the base, which implies that the guy is invariant by all such root spaces. And so it's invariant for almost every. You apply some Ergodic theorem, and you finish. Okay, I think I should stop.
Questions? Questions or remarks? Okay, so let's thank the speaker once more.